So to start off, the Earth rotates around the north and south axes. If the Earth didn't rotate, the pendulum itself would not rotate. The pendulum is the stationary plane in this example, and we are the rotating observers. Where the Earth is rotating underneath the pendulum does not actually rotate with the Earth because it's attached to a string. So it is considered a fixed axis. The pendulum is a heavy weight just attached to a long string so that it can swing back and forth for long periods of time before it stops. If the Earth was not spinning, the pendulum should swing back and forth with no deviation from a straight line. However, because the Earth is spinning, the pendulum will move back and forth, which will cause it to look like the pendulum, if he was drawing a line, the pendulum was deviating and rotating. But instead, the pendulum isn't deviating and rotating, it's the Earth underneath it.
The speed at which the pendulum makes a full rotation depends on the latitude at which the pendulum is swinging. To find out how much a pendulum rotates in a given latitude in 24 hours, we do n equals 360 degrees times the sine of the latitude. At the equator, where the plane on which the pendulum is swinging is orthogonal to the omega vector of Earth's rotation, it will not rotate. At the poles, the plane is parallel to the omega vector. Thus, all it takes is a day for the Earth to complete a rotation. And because we are on the rotating plane, the pendulum will appear to complete a rotation in one day. The pendulum is in a fixed plane because it does not rotate with the Earth, but because we are rotating as on the Earth as it spins, it appears that the pendulum rotates in a day. At latitudes between the equator and the poles, the pendulum will take longer to make a full rotation the closer it approaches the equator, because the J component becomes smaller and smaller as the angle to the equatorial plane becomes smaller and smaller. The I component of the pendulum becomes larger, and we treat the rotation as an angle from the equator plane.
So first we start with the acceleration equation for the stationary frame of reference, which is the pendulum bob, and we have the equation already derived here, and then we can eliminate the centripetal force because it's such a small force, and we can eliminate this part of the force as well since the Earth's wobble is so minimal. So the next part is just to show that the Coriolis is part of this force and what it is. So you start off with the Coriolis part of the force, which is the first part of the cross product, which is omega, is going to just be your magnitude of omega times cosine phi j plus magnitude of omega times sine phi j k. And the reasoning behind this is your pendulum will start moving up and down in the north-south direction, and we're assuming that. And also your pendulum will have some motion in the z direction because it will go up and down towards the surface of the Earth and away from the surface of the Earth, while at the same time maintaining a north-south bob. And so given that, we plug that into the cross product equation, and then we just assume that the velocity vector for the rotational frame of reference will be split into three parts. You have Vx, Vy, and Vz. And given that you can generate the solution, which I wrote here, is the magnitude of omega times cosine phi Vz minus magnitude of omega times sine phi Vy plus the j component, which is magnitude of omega times sine phi Vy. And then you can ignore the k component since it's negligible, considering that there's such a large acceleration due to gravity in relation to all of this. So the k component is simply dropped. And phi is the latitude, as I wrote here. So I wrote the acceleration on the non-rotational frame into its x and y components. So for this, I created a variable p, which is the pendulum acceleration, the natural pendulum acceleration, and then so I have p of x and p of y. And then I also have the written out I component and j components from previously. And in the I component, I eliminated the vz factor because the acceleration on the z-plane is simply very minimal, so that also is negligible. So the next step is to convert this into a differentiable equation. So what we're going to start with is to take the y component of the acceleration and turn it into an imaginary plane, the complex plane, so we can eventually end up with an answer that essentially works and has a real answer. So we have the equation, which ends up being adding the y component multiplied by I and the x component together, which starts off with the acceleration of that component added to the acceleration of the y component added to, I also defined the pendulum acceleration like as being the frequency, the natural frequency squared. So here we have the frequency squared multiplied by x, and here we have the frequency squared multiplied by iy added to 2I times omega of sine phi vx minus 2 magnitude of omega times sine phi vy, and that will end up with, given that n equals x plus iy, this part will be the second derivative of n, and this part will be just frequency squared times n, and this part will be, these two combined will be the 2 times I times magnitude of omega times sine phi times n. So we have our equation from last time, and that's set equal to 0. And upon looking at this, you realize that it's like a second order differential equation, and we're assuming that it has solutions and is homogeneous. And then the next step is to find a solution in the form of e to the negative I alpha t, where you have, based on the second order differential equation, you can convert the second derivative of n equal into alpha squared plus 2 magnitude of omega sine phi alpha, replacing the I times n to the first n's first derivative, and then minus the natural frequency squared, since that simply replaces n as 1 equals 0. And so solving this using the quadratic equation, you get this equation, which is negative magnitude of omega sine phi plus or minus, and then this is the omega squared sine squared phi plus or minus f squared, and then this is the natural frequency of the pendulum. Like, this is very close to the natural frequency of the pendulum, this part under the square root sign, simply because it's much higher. The natural frequency of the pendulum is much higher than the Earth's frequency of rotation. So you can simply ignore this part, since we're only looking for the Coriolis effect, which is this part of the equation. So then you have the solution, which is e to the negative I times magnitude of omega sine phi t, and then you take the real part, which is in the x-plane. So basically you just take the cosine of the exponent of this. So you have magnitude of omega sine phi t equals 1, and then so cosine is equal to 1 on 2 points, which is 0 and 2 pi. So you can assume that the start point is the 0 degree point. So cosine 0 equals 1, and your next point must be your this part must equal to 2 pi, because that's the end position. So then that equals to 2 pi. So then you have your time equals your 2 pi over magnitude omega sine phi. So using the previous equation, we have the Chicago's latitude, which is 41.8781, and then we have the time for full pendulum rotation to, the original angle is 35.96 hours, which we got from another accepted formula. So basically here we have 35.96 equals 2 pi over magnitude of omega sine 41.8781, and we want to get magnitude of omega. So we figure that out, and then in the end we get magnitude of omega equals 0.261744 radians an hour, which is very close to 2 pi over 24, which is the accepted rotation of Earth.